This video is just going to walk you through one more example of optimization. There's going to be something a little bit different than this problem than the ones we did before spring break. This is going to be tied to the assignment on page 388, numbers 3 and 4. The reason I separated 1, 2, and 3 and 4 is because there are some differences in how you should approach these optimization problems. So this example I have is that it says 10 feet of wire is to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? So if I were to draw a little picture of a square, so because it's square and the sides are the same, I'm going to label both of those with X, and then my circle is going to have radius R. And so what I'm trying to optimize is area, and so I'm going to add the area of the square with the area of the circle, so x squared plus pi r squared, and what I'm trying to do is maximize the area. But we are limited. We only have 10 feet of wire, and so in this case it's going to be our perimeter. And so perimeter is 10, and then 10, set that equal to the two perimeter equations of the square and the circle, so 4x plus 2 pi r, and then get one of the variables by itself. So in this case I got x by itself in terms of r. So then I minus 2 pi r and divided by 4, and I ended up with 2.5 minus 0.5 pi r equals x. So when I go back and substitute that into the area equation, I get 2.5 minus 0.5 pi r and then squared plus pi r squared. And then when I do the derivative, I have to do the chain rule. So the derivative of the inside is negative 0.5 pi. And then power rule, bring the 2 down and then reduce the power to 1. And then the derivative of pi r squared is just 2 pi r. So I have to set that equal to 0. After I've simplified it, the negative 0.5 and the 2 multiplied to negative 1. So set that equal to 0 and solve for the radius. And so in this case, I get the radius to be 0.7. And then on the next page, I am going to perform the first derivative test to see what happens before and after 0.7, just to see if this is a critical point and if it's doing what it should both before and after 0.7. So if I make a number line and I plugged in 0.5, so that's before 0.7, and I plug in 1, which is after 0.7, my number line is just telling me that my function is decreasing before I get to 0.7 and it's increasing afterwards. And so this implies that it's actually a minimum, not a maximum, and we're trying to maximize area. So let's just double check it. If I do the second derivative test, I get that this is greater than 0, meaning it is concave up, and once again that it is a local minimum. So you guys asked me the question before spring break, you know, what happens if the test doesn't verify that it is a maximum or a minimum, and this is one of those examples where it's not going to. And the reason is because we have two different shapes that we are talking about, a square and a circle. And so we have to use the closed interval method. So this is the extreme value method. So because we get a minimum and that first and second derivative tests don't back up our work, we need to double check the end points. So we've just done the critical point, 0.7. Now we have to check the endpoints, meaning what are the lowest values that we can plug in, those endpoints, into the function to see if we get a maximum area that way. Well, think of it this way. If I use all 10 feet of wire for this circle, so 10 equals 2 pi r, that means the radius can be as large as 1.592. So that's the interval of just the radius of the circle. But then if I think about the square, if I just use the 10 feet for the square, 10 equals 4x, divide by x, that means the x value can be between 0 and 2.5. And so what I'm going to do with the closed interval method is the first thing I did was plugged in 0.7. And when I do that, I get an area of 3.499 feet squared. Well, according to our first and second derivative test, 0.7 is not a maximum. So now I want to plug in my endpoints. So this 1.592 into the area formula and see what I get for an area. And then I'm going to plug in the 2.5. You don't need to plug in 0 because those are, when r is 0, your x is 2.5, and when x is 0, your radius is 1.592. So those are the two endpoints that we're going to use. When I plug in the radius of 1.592, I get 7.962 squared feet. And now plug in an x value of 2.5. I get an area of 6.25 feet squared. So according to the extreme value method, also known as the closed interval method, my absolute maximum occurs when my radius is 1.592, not when it is 0.7. And so this is telling us that we should use all of the wire for the circle to maximize area of 7.962 feet squared. So we're not actually going to use a square in a circle because our objective was that we wanted to maximize area. Well, in order to get the largest area, we should only use the wire for the circle and not for the square. So these optimization problems, when you have possibly two shapes or one variable dependent on another, you can't just assume that the critical point is going to be your absolute max or absolute min. It's possible that this could have been a local maximum but not the absolute maximum. This is where we're going to use the closed interval method or the extreme value method, where to find the absolute max, I plug in the critical point and plug in the endpoints to see if which one does give us the largest maximum or the largest area. It can also work with a minimization problem. So this is an example of optimization where there is going to be some other constraints like domain on the two variables, and this is more similar to the problems on page 388, numbers 3 and 4. So attempt those homework problems tonight and come in with questions tomorrow. Have a good night.